Resetting. Good afternoon or evening or whatever time it is where you are, and welcome to Turbo Intruder, abusing HTTP misfeatures to accelerate attacks. Last time that you made a serious effort to hack into a website, I wonder how many requests did you send? In between brute forcing files and folders and usernames and passwords and maybe even virtual hosts, you probably spent quite a long time configuring and running brute force attacks and probably sent quite a few requests in the process. And I do too, but every time I stop an attack, I find myself wondering if I'd left that attack running for a few more minutes, if I just sent an extra few thousand requests, would I have found something crucial? Would I have found that incredible file that was basically just a backdoor to the server? Or perhaps if I just sent my requests an extra 20% faster, maybe the server would have just gone crazy and started dumping access logs or memory into the response for me, like this one here. And I'll never know, but in this session, I'm going to introduce a tool designed to solve our brute force problems by using a custom HTTP stack designed to send requests as fast as possible. First of all, I'm going to talk about what makes Turbo Intruder so fast and how you can make your own tooling equally fast if you want to. Then I'll do a live demo on how to use it, which hopefully won't have any side effects on the live stream performance. And then I'll talk about some of the other cool features that Turbo Intruder has other than simply running really quickly. And after that, I'll hopefully have time to answer maybe 10 minutes of questions. So, traditionally, tools designed for brute force have focused on achieving speeds through having tons and tons of concurrent TCP connections. And originally, this was done by having loads of threads, but more recently, you'll see some of these tools using asynchronous network stacks. So that means they aren't putting so much load on your CPU with tons of threads, but they're still running through what's fundamentally the same process, which is they spend ages doing this TCP and TLS handshake before sending their request and reading in the response. Now, this approach is incredibly wasteful of time and bandwidth, and it actively creates bottlenecks that don't even need to exist. So what I'm going to do is I'm going to kind of zoom in and focus on getting the best possible performance with one concurrent connection, and then scale up the number of threads later on. Now, is anyone familiar with a web security scanner called Skipfish? It's a few years old, but, well, if you've ever used it, you will know this tool is ridiculously fast. The first time I ever ran it, it just took out the server almost instantly. It was amazing. And Skipfish is what inspired Turbo Intruder because it proved that things could go so much faster than how fast most tools run. And originally, I thought, okay, Skipfish is so fast because it's written in C by Tough. And that is part of the reason why it's so fast, but I dug into it and it looks like the core is that Skipfish reuses connections, just like web browsers do. So rather than doing one TCP and TLS handshake per request, it will do the handshake once and then send as many requests as possible over that connection, which vastly reduces the bottlenecks. And with a single thread, that leads to a roughly 400% speed increase over the normal approach. So that's why Skipfish is so fast. And the very first version of Turbo Intruder was simply a hacked up version of Skipfish's code. But then I found something that let me make Turbo Intruder even faster. And that is an old school technology called HTTP pipelining. Now, HTTP pipelining is not used by any modern browsers as far as I'm aware, but it is supported by the majority of servers. And it works roughly the same as Skipfish, where you just send lots of requests over the same connection. But instead of sending one and then immediately reading the response, you send all of your requests back to back before you bother reading in any responses. And that has the effect of greatly minimizing the effect of latency and server processing time on how quickly you can send your requests. So it almost makes it like running a brute force attack on a local server. And using this technique with Turbo Intruder, with a single thread, I was able to get a 6,000% speed increase compared to the original technique. And this is so fast that it puts us in a really great situation where the number of concurrent connections that we have, like the number of threads, is no longer the bottleneck for how fast we can run. And that's wonderful because multiple servers and firewalls implement rate limiting by constraining the number of concurrent connections. But we can, using a tiny number of connections, still send requests really, really fast. So after I got pipelining working, I was like, okay, that's cool. I wonder if I can make this even faster by using an asynchronous network stack rather than threads. But actually, because this technique is so fast by itself, making it asynchronous made virtually no difference. And I also tried HTTP 2, and likewise, HTTP 2 didn't go any faster. So I ended up dumping that code, and we're just using old-fashioned threads. So that is pretty much all the theory. So now let's just have a look at how we're going to use it. First off, after installing Turbo Intruder, which you can do via the BAP store. In fact, in theory, you can do it right now and follow along, hopefully. Anyway, you select where you want to inject in the request, and you right-click and click Send to Turbo Intruder. That will pop open a window that looks something like this. So you've got your request in the top half and a snippet of Python code in the bottom half. Now, don't panic if you're not too familiar with Python. This code barely needs to be tweaked most of the time. So you don't need great Python skills to achieve whatever you need. You might also be thinking, hang on a second, if I wanted to code Python, I just use the requests library. Or whatever Python library you use, I can almost guarantee it won't support pipelining. And even if it does support pipelining, it certainly won't support sending malformed requests. And as hackers, we will want to be sending malformed requests. Whereas Turbo Intruder's network stack, it just uses sockets. It's coded by me, and it lets you do pretty much whatever you want. So now let's take a closer look at this Python code. To begin with, we've got the code that sets up the networks stack, and you could leave this as is for almost all the time. But if you want to get the maximum speed possible, then you'll want to tune these parameters here. So I'm going to demo that shortly. After that, you'll want to start the engine and open your word list and start queuing up your requests. Now, because we're starting the engine and then queuing the requests, this is a streaming attack, which means it's pretty low on memory usage too. The final thing that we need to code is this handle response function. So in Burp's normal intruder, every response that you get from the server gets put in a giant table. And this approach isn't really plausible for Turbo Intruder because at the speeds that Turbo Intruder runs, the table will get ridiculously large and you'll run out of memory really quickly. So instead, I've made this handle response function, which is a callback, which gets invoked every time that you get a response from the server. And in this, you can write a tiny snippet of code to decide whether this particular response deserves to be added into the table or not. So here's a screenshot of an attack run on a home computer with a normal residential router, just like the rubbish one that BT sends you, attacking an internet server sending HTTPS requests. If you look at the status bar, you can see this attack has been running for 17 hours. I ran it overnight. It sent an average of 22,500 requests per second during that time for a total of 1.4 billion requests. And because this is a streaming attack, the memory usage during that time is pretty much flat. At the time that I took that screenshot, it was flat at 3 gigabytes. Since then, I've made some optimizations, and with a bit of luck, you'll find it uses about 1 gig. And thanks to all of that, you can see in the top half, we've successfully brute forced a completely random 7-character file, which is not something that I think you could achieve with pretty much any other tool out there, let alone in this space of time. So let's take a closer look at this tuning process. So now the live demo begins and things potentially get a little bit more exciting. If you look at the screen, you should now see Burp Suite. So I'm going to select my injection point and right click and click Send to Turbo Intruder. And you can just see where I selected has been replaced with a %s, which is simply the injection point. This is where the payload is going to go. So I'm going to start out sending these requests to Hacksaw, which is my game on the internet, and sending 1 request per second per connection, just like Burp does, with 1 concurrent connection. In other words, 1 thread. This is just to get the kind of baseline speed. So you can see here, we're doing around 18 requests per second. So now we're going to try and optimize these values to run as fast as possible. First of all, I'm going to change requests per connection to 200. So this is reusing the connection as much as possible, roughly like what Skipfish does. So if I set this running, you can see I've immediately jumped to 80 requests per second. So we're running about 4 times as fast with just a single concurrent connection. So that's kind of cool, right? So now I'm going to try to, oh yeah, sorry. One thing I meant to mention. Okay, so this is doing 80 requests per second, which is good, but this retries count is slowly going up. And that doesn't mean we're losing any requests because they are being retried automatically, but it's an indication that we've set this value kind of too high. So we're going to try and reduce it slightly. So if I change this to 100, the server is going to stop dropping the connection. And with any luck anyway. Yeah, and so we've got the same speed, but the retries count is flat on 0, which means this attack is more or less optimal as far as the number of requests per connection goes. Okay, so that's that. Now let's turn pipelining on. I wonder how fast do you think this was going to go? It was doing 80 requests per second. How fast is it going to go now? Let's see, shall we? Oh, that's cool. It's doing around about 1,100 requests per second. So it's going over 10 times faster than the previous technique and over 400 times faster than the original technique. And as a result, we've actually found something here. Our brute force has located a file. So that has maximized the speed per connection. And now I'm just going to increase the number of concurrent connections. Now, based on some testing I did earlier, 20 is about right for this situation. Generally, you're going to want a value in between like 1 and 30 here, I think. So if we set this running, you can see we've jumped to around about 9,700 requests per second. I think we can do slightly better. Let me just try this again. Let me try 25. It's pretty variable. You can see we're pretty much doing exactly the same speed. So 10,000 requests per second is about the maximum speed that we can hit on this setup, but that's still really not that bad, especially bearing in mind these are HTTPS connections. And therefore, if we leave this running for a few seconds, then we find the final file, which is at the end of the word list. It means we've sent all 235,000 requests in that 25-second period. So that is the live demo. That's how you tune it. Obviously, if you don't need speed, you don't need to bother tuning it. Now let's try and get the PowerPoint back. Boom. Okay. So I've just been showing you how to do streaming attacks, which are great for long-running attacks where you want to minimize speed and maximize speed, minimize memory usage. However, if you want to find a race condition, then a streaming attack is the opposite of what you want. You want all your requests to hit the server at the same time. So here you can see the code's changed slightly because I'm calling engine.start after I'm queuing all the requests, and the number of concurrent connections is equal to the number of requests that I'm queuing. So that means we're going to establish all those connections and then send all the requests at exactly the same time. So they should hit the server at very close to the same time. Why might you want to do that? Well, it can cause interesting things to happen. For example, here we're on a shopping cart on a bug bounty site. We've got a cart total of $65, and I've got a single-use coupon, which should give me some store credit. But I've successfully applied this a whole bunch of times, leading to a total discount of $84, leading to an end final price of -$19. So that's a pretty good Turbo Intruder discount. So that is the core of what Turbo Intruder is all about. But while using it in my testing, I found that making best use of it involves quite a few steps. Each of these is something that you have to do manually when you use it. And I think all of these steps can be fully automated. But to begin with, I just picked the most annoying and tedious step, which is coding the response screening function, coding the callback to work out what should go in the table and what shouldn't. So what I've done is implemented a fully automated solution, which will basically handle this side of things fully automatically for you almost all of the time. So if you launch Turbo Intruder, you should see the default script, which looks something like this. And the key part is these engine.q lines in the middle that have this learn parameter. What the learn parameter says is it tells Turbo Intruder to learn the response to these requests as being boring. And if any future response is deemed as boring, then the interesting parameter in the handle response callback will be set to false. So by teaching it to learn a random string response as boring, we're effectively filtering out all 404 pages and the like, without you, the user, actually having to figure out what the 404 page really looks like. Of course, you can play with this yourself if you like. So for example, maybe they've got a web application firewall and it blocks every request with the word admin in. Well, you can say, please learn the response to a blocked request as being boring, and then you don't need to worry about it turning up in your table anymore. So this is completely generic code, which you generally shouldn't have to change. And the end result is, with no work, you get automatic free handling of stuff like custom 404 pages. And not only that, but enumerating basically anything, even if it's a username or host or cookie, header, file, folder, or root. Basically, as long as the valid value gives you a significantly different response from an invalid one, then Turbo Intruder will automatically be able to spot the valid ones and put them in the table for you. And this is based on logic from /parrot scanner, and as such, it's capable of spotting some really quite subtle stuff. For example, on one site, on a bug bounty site, I found if you try and log in with an invalid password lots, the account gets locked and it says your IP has been locked out. Please enter a correct username or password. But if you enter the correct password when the account is locked, it says this account is locked, but it no longer tells you please enter a correct username or password. So you can use that to successfully brute force someone's password, even though the account is locked, and then just wait 5 minutes and log in. And that kind of really subtle difference in the response is something that Turbo Intruder's diffing is completely capable of noticing and flagging for you. Right, there's just a few other random features that I'd like to mention before I wrap up. So one of them is this word lists.observed words feature. So this is a built-in word list, and the word list contains every word that Turbo Intruder has seen in your proxy traffic. So that means basically loads of keywords from the website that you've been testing. And that can lead to all sorts of interesting findings that you'll just completely miss if you rely on using a static word list. Another cool feature worth highlighting is that in the handle response callback, you can use rec.engine to queue up more requests, which is useful if you want to send some kind of complex multi-step attack. And here in this specific example, we're using it to do a recursive directory brute force. The one other thing to mention is by default, Turbo Intruder will use my network stack, which means it's really fast, but you miss out on some core Burp features like handling of upstream proxies and SSL client certificates and that kind of stuff. If you want those features combined with the features of Turbo Intruder, then you can stick engine equals engine.burp in the first line there, and that will mean it will use Burp's network stack. So it will run slower, but you'll get the rock solid stability and other cool features offered by the core Burp stack. So that's pretty much it. The three key takeaways, the three key things you should definitely remember are that billion request attacks are now absolutely plausible. Bandwidth is not your bottleneck in the vast majority of cases, and you can install Burp you can install Turbo Intruder via the BAP store, or download the jar from the GitHub if you want. Okay, cool. So now I'm gonna, oh yeah, don't forget to follow me on Twitter. Thank you. If you ask any questions you have in the YouTube chat or on Twitter, I'm gonna try and answer those.
Yeah. Thanks for that, James. And what we've said there, you know, anyone who's following along or anyone who's watching this after the fact, James's handle on Twitter, do you want to just share that with the audience real quick, James?
Albinowax.
All right. How do you spell that? Just in case you don't know.
It's on the slide, hopefully. Yeah.
There you go. Perfect. Yeah. Good. Yeah. And, you know, beyond that, anyone who's listening right now, if you want to pop some things into the YouTube chat, we can have a quick Q&A at the back of this. There's a couple of questions already. So James, one of the questions that came out early on in the piece, and you kind of addressed it, but it'd be interesting to hear you dive into it a little bit more. Like, what kind of router can handle this? Like, what kind of bandwidth do I need upstream to be able to make full use of Turbo Intruder? That are running things from VPS or from different parts of the world, whatever else. There's a lot of variability there. So how does that play into it?
So all my testing has just been done over a normal residential connection. I think the key thing to remember is that HTTP requests are really small compared to like streaming films and stuff. So the bandwidth usage isn't really that high. And yeah, I would mention, so Turbo Intruder can be run from the command line. So you can put it on your VPS and run it from there. If you want to do like a 2-week attack and send thousands of billions of requests, then you might want to do that.
I guess it's
very cool. All right, another question is, what sort of real-world performance enhancements have you seen, you know, really in the wild? Like, often the speed of the application seems to be the bottleneck. And the question is with respect to what you've seen in the past from the previous versions of Intruder.
It varies hugely depending on the server that you're testing. So like that server that I demoed it on is my own server, but it's a real web server. It's just running at Nginx. It's not particularly powerful. And on that, I could go, the Burp Intruder would do maybe 500 requests per second to it, and I was able to get Turbo Intruder up to 30,000. That's the best kind of bonus that I've seen, but it's pretty common that you should be able to get several thousand requests per second to a server without too much trouble.
So your mileage is going to vary depending on the application at the other end, but there's a consistent increase that you
that's the key factor. But even if your connection sucks, Turbo Intruder will still go faster than other things just because it's more economical with the network stuff.
Perfect. So another question, and again, you kind of tapped on this when you were talking about balancing the retries with the attack rate or the attempt rate. But just to tap back into it, how dangerous or heavy is this against production servers? Like, what's your kind of, you know, knock the box over experience against a single host Apache or Nginx server, for example?
To be honest, I haven't done very much testing of that side of things. I think basically you need to be mindful of what you're doing. The classic thing that Nginx would do, that Skipfish would do, is it would send loads of requests, which would lead to the log files getting absolutely hammered, and the disk would basically die.
Yeah, totally.
So I would definitely be mindful. If you use it with a small number of concurrent connections, it will be really obvious when the server starts to struggle. Something I'm looking forward to in the future is something that basically checks the health of the server and then slows down automatically.
That would be awesome. It's you know, it's a funny topic that comes up around, you know, the typical exclusion of denial of service or DDoS attacks in bug bounty terms. And, you know, one of the reasons, especially for DDoS, is that it's just, you know, physics, that if you've got a big enough thing that you're hitting something else with, then it's going to break. So it's really, it's kind of an exercise to the reader at that point. So one last question here real quick, and thank you for that answer. I think that's really cool. Seeing that feature where there is some sort of, you know, dynamic kind of feedback loop or rate limiting based on how the server on the other end is performing would be a very cool tool for something that would help, especially newcomers with how to do these types of things. But last question here, is there any wildcard handling support when the server returns 200 for everything? So you were talking about some of the kind of, you know, dynamic understanding return content that you guys have built. How does it handle that particular scenario?
So that automatic handling is based on /pad scanner, and if you Google /pad scanner, you'll find a whole white paper covering in great detail how that stuff works. But it's absolutely not just looking at the status code. It looks at tons and tons of things like the status code, the content type, the word count on the page, the number of bytes on the page, the occurrence of certain keywords, content length, the number of new lines, loads of different variables, and it just filters them to find out which ones are stable and then use those.
I'm really excited. Folks on the platform over the last year have done a lot of really great
Sorry,
stuff.
James, go ahead. Sam's using another talk right next to me, so it's bleeding through to my mic right now. Apologies.
Hey, James, this is Jason. One of the ones that was kind of in the between the lines here was, does it support multiple insertion points like the normal intruder does?
Okay, so you can basically it only supports one insertion point, sort of, but you can queue. You've just got some Python, right? If I scroll back, so that target.rec value is just the request, so you can queue up completely arbitrary requests. You don't have to use the insertion point system. It's purely just there for convenience.
Okay, thanks.
All right, beautiful. So, I mean, with that, you know, thank you so much, James. It's very cool to see what you guys have done here. You know, it's sort of reminiscent to me of what Robert Graham did with, or to Nmap rather, when he released Masscan, like some of those tweaks around efficiency of you know, response. It feels a lot like that, but the web version of it. So, congrats on you know, having it work. I know that part's hard as well. And actually seeing it drop and get in front of a group of people. At this point, we are going to wrap this talk up and pause for a couple of minutes while we set up for SEM. So thank you so much for listening. And again, you know, follow James on Twitter, jump into the conversation. Any other questions that you'd like to get answers to, if you're watching this offline or after the fact, or even if you're online, you can get your question answered, chuck it on Twitter and we'll do our best to get to that as well.